In the last screencast, we talked about pressure and how it's related to weight of the air column. And at the end of that discussion, we talked about pressure at the ground, i.e. the surface pressure, pressure at the surface of the Earth. And we talked about how the pressure at the ground is related to the weight of the whole air column and how that in turn is related to convergence and divergence of mass into the column. So with this screencast, I want to stick on the theme of the surface pressure. And in particular, I want to talk about when we have data of pressure at the ground, how we represent that data in the form of pressure maps, what are called surface pressure maps. And the idea is that we've got a bunch of places that measure pressure. So individual places, stations that measure pressure. So we've got weather stations, we've got airports, we may have schools, things like that, all of which are reporting pressure measurements. And so you can see, for instance, maybe we might have something like this figure over here on the right. And so what this is a bunch of measurements. So we're looking down from above here. So we've got north is this direction to the top of the screen, east to the right, west, and south. And each of these individual dots is some place, some location that's measuring the pressure. So we might have Easterwood Airport here in the middle. Maybe this is Navasota down here, maybe Somerville, so forth and so on. Each of these individual places is measuring and reporting the pressure. Now, in this particular case, we've only got 7 measurements of pressure. But even so, it's kind of a little bit difficult to very quickly look at these numbers and get a feel for what the pressure distribution looks like in this area. And you can imagine if you had, instead of 7, if you had 500 measurements of pressure, it would be really difficult to look at all those numbers and get a feel for what the pressure field is. And so instead, what we like to do is we like to take all these numbers and turn them into a graphical representation, a visual representation that'll allow us to just glance at it and quickly get an idea of what the pressure distribution looks like. So how do we do that? Well, the way we're going to do that is we're going to draw curves on our data that are called isobars, curves called isobars. Here, the prefix iso refers to equal. So iso is a prefix that means equal. And you'll remember that bar is a unit of pressure. A bar is a unit of pressure, and millibars is 1,000th of that unit of pressure. So what this is then, isobars are curves that represent places where we have equal pressure. So everywhere along one of those curves, we have the same value of pressure. That's what we're aiming for. So for instance, given this data over here, we can see that 2 of our stations have pressure of 1,004. So if we were to draw an isobar on this map for 1,004, so a curve where the pressure takes the value of 1,004, that curve would have to pass through these 2 stations. It might end up looking something like this. So everywhere along this curve, the pressure has a value of 1,004, and so it ends up going through the 2 stations. Now, of course, you have to figure out what the shape of the curve is going to be as it passes through those stations, and we'll talk about that on the next slide or two. But that's the basic idea. Everywhere along this curve, pressure has a value of 1,004. And then if you wanted to draw another curve where pressure takes the value of 1,008, say, well, we've got a station with 1,008 here, so it's going to have to go through that, and it might end up looking something like this. So now again, how I figured out the shape of this curve after it goes through 1,008 is what we're going to talk about. But the main idea is that along this curve, everywhere along this curve, the pressure takes a value of 1,008. And then, of course, we could do 1,012, and so forth and so on. So 3 isobars in this case. One where the pressure is 1,004, one where the pressure is 1,008 everywhere along that curve, and another where pressure is 1,012. So in the end, what I've done is I've taken that pressure data, which can be kind of unruly and difficult to manage, and I've turned it into a pretty simple graphical representation that's easy to interpret. So in this case, I can see that the pressure is lower down here, just at a glance, and that it's increasing as I go across the contours in different directions. I cross 1004, cross 1008, so forth and so on. I cross 1004, 1008, and so the pressure increases as I go outward away from this lower right corner. Okay, so now let's talk about how we actually draw in these isobars, in these individual contours. So let's think about the isobar that represents 1004 millibars first, since we have two stations with values of 1004, specifically these two guys. So we know that when we draw our 1004 millibar contour, it's going to have to go through those two stations. But how does it get there? There's a lot of different ways we could connect those dots, right? We could connect the dots this way. We could go around the other way. How are we going to figure out how it is that we're going to connect those points that have 1004? So what do we do in between? Well, in order to figure out what we do in between, where to go in between, we have to look for pressure measurements that bracket the value that we're interested in. So in this particular case, for instance, we have a pressure measurement of 1000 here, and we have 1006 up here. So the contour that we're interested in, 1004, is in between those two pressure values. So we know that the contour is going to have to pass somewhere in between those two stations. You can think of this as if you started in your car down here at this station, and so what was this? This was our Navasota station, and you're driving up towards Easterwood Airport. You start off down here at 1000 millibars, and that actually would be a big pressure change for that short distance, but you get the point. You start down here at 1000 millibars, and you're driving up towards the other station, and the pressure is increasing. It's increasing, it's increasing, it's increasing, until when you get to that station, it's 1006. Well, somewhere along that drive, the pressure went through 1004 before it reached 1006. We just have to figure out where it reached 1004. So how do we do that? Well, the first thing to note is that between these two stations, if we start at 1000 sort of as our anchor point, then between 1000 and this other station, 1006, the pressure increased by 6 millibars. So there's a pressure increase of 6 millibars. So in order to figure out where we're going to be, we need to figure out what fraction of that 6 millibars occurred. So what fraction of that 6 millibars is the difference? Well, so let's just draw it out for you. Actually, I'm jumping ahead of myself just a little bit. So I'm going to back up one step here and point out. So again, the basic game here is we're looking for 1004. We know that it has to go between 1000 and 1006, and we're trying to figure out where. Now, I should point out that in a strict sense, we don't know where it's going to be, right? Because we have no measurements there. So there's no way for us to actually know where the pressure in here is 1004 because we're not measuring it. So we have to make an assumption. And the assumption that we're going to make is that the pressure varies smoothly over this region. That is, we're going to assume that if we start down here at 1000 and we drive our car up towards 1006, we're going to assume that the pressure is increasing at a steady rate. It's a nice smooth transition in pressure. So once we make that assumption, and that's probably a pretty good assumption if you have enough measurements. If you have enough measurements to represent the pressure field well, you can probably assume that between any two stations, the pressure is varying fairly smoothly. Okay, so again, let's take this analogy of driving from 1000 to 1006. The first step is to recognize that as I'm driving along that path, the pressure increases by 6 millibars over the full path. And remember, we're going to assume that the pressure is increasing smoothly, so at a steady rate. And so then we just have to figure out, at that steady rate, where do we hit 1,004? So to do that, the calculation that we have to go through looks something like the following. We'll assume that 1,000 is our anchor point, and we want to figure out how far we have to go from 1,000 to get to 1,004. So I'll just sort of symbolically represent that as distance from 1,000 millibars. Distance from that station, 1,000 millibars, that we have to go to get to 1,004. So the first thing we have to say to figure out is how much does the pressure have to increase to get to the contour we're interested in. In the present case, that contour is 1,004, so the increase in pressure that we need to get to the contour is going to be given by taking, I'm having trouble speaking here today. It's going to be given by taking the difference between our contour value and our starting point. Right, so we take 1,004, that's the contour we're interested in, subtract off our starting point from our anchor station, and that's the pressure difference that we need to get to our contour. And then we can just divide that by the full pressure difference between the two stations, and that's going to tell us the fraction that we need to go in order to get to the contour. So in this case, we'd be dividing by 6 millibars, which is the full pressure difference between the two stations. So again, if we start at 1,000, to get to 1,004, we have to increase by 4 millibars. We divide that by the full difference between the two stations, which is 6 millibars. And that tells us that how far we have to go to get to our contour is going to be 2/3 of the difference between the two stations. Right? We're assuming it increases steadily. We have to go so that it increases 4 millibars. The full difference is 6 millibars, and so that's 2/3 of the distance between the two stations. So then we're going to assume that our point where we hit 1,004 is going to be right there. It's going to be 2/3 of the distance starting at 1,000. 2/3 of the distance, bang, right there we hit 1,004. Now from there it's pretty easy because now we've got 3 points where we have value of pressure of 1,004, so we just have to connect them. So I'm going to erase my 6 millibars just to get it out of the way. And I can just draw on a contour that connects my 3 points where pressure is equal to 1,004. And I end up with a contour that looks like that. So that's my contour for 1,004 millibars. Now, if I wanted to do 1,008, I just have to play the same game. So for instance, for the case of 1,008, we've got one station down here that measures 1,008. So we know that we're going to have the contour go through that station. To figure out where it goes from there, we look for stations that bracket 1,008. Well, we've got 1,006 and we've 1,012. So those guys bracket 1,008, and 1,008 is somewhere in between. As before, the full pressure difference between 1,006, starting at 1,006 and going to 1,012 is 6 millibars. To get to our contour, starting at 1,006, we need to go 2 millibars to get to 1,008. So our fraction of the distance is 2/6, which is 1/3 of the distance. So it's going to be something like that. So now we have 1,008 at those 2 points. We also have 2 more stations that bracket 1,008. We've got 1,006 and 1,010. In this case, 1,008 is halfway in between, so we can split the difference with our point. Now we've got 3 points. Those are the three, really the only 3 that we can draw here. I guess actually we could do one more for these 2 stations if we wanted to. But we've got 3 points in here, so I'm going to go ahead and draw in my contour, and it's going to look something like this. And then finally, if we wanted to do 1012, well, we don't have a whole lot of data for 1012. We've got one station that measures 1012, and we don't have any stations that bracket it. So we just have to, for the present case, since we don't have any more data, we just draw in a curve that kind of looks more or less like the other curves. So it's kind of something like that. And so if you take all of your data and you go through and repeat that set of steps, you can convert your data from a bunch of numbers into a graphical representation that's much easier to read. Now, one thing I should point out about this is that when you're drawing contours, you always want to be taking the same interval between your contours. That is, we drew a contour for 1004. The next one was 1008, which was an increase of 4 millibars. And the next one was 1012, which again was 4 millibars. So that way that you know that anytime you go from one contour to the next, you know how big the pressure difference is without having to go through and read all the numbers. You know that it's going to be a 4 millibar jump from one contour to the next, and then another 4 millibars to the next contour. So it makes it much easier to read the graph if you know how big the jump is between each individual contour. So make sure that every contour has the same jump to the next contour and so forth and so on. Same difference in pressure. The second thing to point out about this is that although I drew this in for pressure, isobars, I could have done this for other fields as well, for other physical properties as well. For instance, I could have taken all of the temperature measurements at these same stations and drawn in curves that have the same value of temperature. Those would be called isotherms. I could have done relative humidity and so forth and so on. So pretty much anything that you're taking measurements of at all these points, you could do the same exercise and draw in all these curves. The last thing I'll point out about this is that in the old days, this is actually exactly how it was done. You know, people would get all the pressure measurements on a big map. They would sit down and they'd look at all the different values of pressure and try to find places where the curve should go in between all of these measurements. You know, they'd find bracketing values and figure out where between those stations it should pass. And then they'd look at all the other stations and do the same thing. It's a very somewhat difficult and tedious process to do that. Nowadays, computers do it for us. It's fairly easy to write algorithms to do that kind of thing automatically. So when we look at pressure maps nowadays, they're not going to be analyzed by hand like this. They're going to be analyzed by the computer, but the computer is applying the same kinds of rules to figure out where this contour should go. Okay, so that's drawing maps to represent your data values. Now, let's get back to this caveat that I mentioned at the beginning, which is that, in fact, when we're looking at surface pressure maps, we're not actually looking at values at the ground. We're not looking at the exact data that's measured at those stations on the ground. And the reason for that is, when you're comparing pressure at different locations, you always want to be comparing pressure at the same height. The idea is that pressure decreases as we go upwards through the atmosphere. So if you're comparing pressure at different heights, the one that's higher is almost always going to have a lower pressure. And so you don't get as much information about how pressure changes from location to location because the higher one is just always going to be lower. So you always want to be taking pressure and comparing it at the same height to make a fair comparison. And when we're drawing our surface pressure maps, the height that we choose to compare the pressures at is actually sea level. They're often referred to as sea level pressure maps. So if we have a surface pressure map, it's actually pressure at sea level. Now this actually raises a complication for all of you guys who live in mountainous regions. Probably not too many of you guys, but there are lots of people who do. And for all of them, this raises a complication. So what if I live in Tibet? What am I going to do? I got a measurement up at, 5 miles or something. So what am I going to do with that? Am I just not going to participate? Well, what you have to do is you have to take, if you have a measurement high above sea level, you actually have to adjust that measurement to get some equivalent pressure at sea level. So if you live in mountainous regions, you have to take the pressure that you measure and adjust it to get an equivalent pressure at sea level by doing what's called an altitude correction. An altitude correction for the pressure to get the value down at sea level. The basic idea of this correction is it tries to estimate if you had, so you're living up in Denver, say, which is a mile high, you've got a mile of dirt between you and sea level. What this pressure correction tries to do is it says, instead of having all that dirt, what if it was air? How much would that air weigh? And then I add in that weight to my pressure, and that gives me an equivalent pressure at sea level. So that's how the game is played. You have to try to estimate what the column of air would have weighed in order to get the pressure down at sea level. So for instance, let's suppose we've got an island with a couple of mountains on it, like this one here. And we've got different places here that are measuring pressures. We're measuring 1,000 millibars down here at the coast. That's basically sea level. Up at the top of the mountain, well, that's way up here. That's what, 1.1 kilometers above sea level. So obviously you're going to have a lower pressure. You're always going to have a lower pressure up here, and it's 894. So it's more than 100 millibars lower. Then you've got one down in the valley, and then another one up here, and so forth and so on. And so if I want to make a fair comparison, I've got to take all of these measurements that I made at different altitudes and adjust them down to the sea level values so that I can compare them at the same height. So this one here, and that's actually what this middle pane is down here. So this gray pane in the middle is the value that you get after you adjust the pressure down to sea level. So this guy down here on the coast, that's easy. That's basically at sea level, so I can just take that as my pressure value. My pressure value is 1,000 down here. Now I've got this guy up on top of the ridge that had the low pressure because it's really high up. So I have to go in and say, well, if instead of having all of this dirt down here between me and sea level, what if instead I had a column of air? How much would that column of air weigh? In the present case, they're estimating that that column of air would weigh 110. So you add that into your pressure, and you end up with a pressure of 1,004. That's your equivalent sea level pressure. So I took my pressure up on top of the mountain and adjusted it to get an equivalent sea level pressure. And I do the same thing for the other measurements. I take each of the individual measurements, try to figure out what the column of air below it would have weighed. In this case, it's 60 millibars, and add that in to get my pressure at sea level. And then this bottom panel down here is the resulting map. So this is showing a bunch of values of pressure, so a bunch of stations in addition to the stations that are shown above. And these are all values of pressure that were adjusted down to sea level. And once I have all those values of pressure, then I can go in and draw contours just like we did on the previous slides. Now, if you're thinking about this carefully, you might realize that this is a little bit of a hack because, if you're up on top of this mountain, you don't have a column of air below you, so there's no way to know exactly what that column of air would have weighed. It depends on the temperature and the density. And so what you have to do, there's actually various different ways to do this, but what you have to do is you have to kind of look at the conditions around you. And then from those conditions, you have to get an idea of what the column of air would have weighed, and then you have to add that in. So you just have to do the best you can. If you're in the middle of the continent in Denver, it can be a little bit difficult to do that, to figure out what that column of air would have weighed. But you just try to figure it out as best as you can. You add that in, and you get your equivalent sea level pressure. So there's no perfect way to do this, I guess is what I'm saying, but you do the best you can. Now, once you've done that, once you've adjusted all your pressures down to sea level, you're likely to end up with a map that kind of looks like this one over here on the left. That is a pretty noisy map. for two reasons. The first reason is this altitude adjustment. Again, there is no perfect way to do that. So every time you do one of these corrections, you're going to introduce a little bit of error. And so that's going to produce a little bit of noise. The second reason is that there's also a lot of sort of smaller scale things going on that'll produce fluctuations in pressure, smaller scale weather systems that produce fluctuations in pressure. And when we're drawing a big map like this one, which is showing the whole US, we don't care about all those little local things. Those are just introducing noise into our map. And so for both of those reasons, the raw pressure maps that you produce are likely to be a little bit noisy. So before we actually show this map to the public and use it to make inferences, typically we put it through some sort of smoothing process. And that smoothing process will take this noisy data and convert it into something that has a much smoother representation. And so it's a lot easier to look at that data and figure out what the trends are, where you have higher pressure, where you have lower pressure. So in this particular case, after we've smoothed the data, it's pretty easy to see that we've got a low pressure center here sitting over, Nevada, Arizona type, New Mexico, whatever that state is there. I'm not really good with the geography. My students always made fun of me of this in the brick and mortar sections because I'd always get the states wrong. I'm getting better at it, although I'm not 100% sure. Is that Kansas? I think it might be Kansas. Anyway, luckily I'm not a geography professor. And so you've got low pressure here in this region of 1004. And you can see pretty simply that pressure is increasing as I go out in the various directions. And just as in the map that we showed earlier, the pressure increase between each contour is 4 millibars. So I know that this one is 1008, the next one's 1012, and so forth and so on. And so I'm crossing 1, 2, 3, 4, so that's 16. So this must be 1020. We've got a high pressure zone down here over the Mississippi, Alabama, and Florida Peninsula region. We've got an even higher pressure up here over the Great Lakes. You can see how the pressure varies in between here. It's very easy to see. And over here, pressure increases a bit, and then it goes back down to 1004. So we've got it going up to 1012 and then back down. So the main point is that we've taken all of these pressure measurements and we've processed it, and we've ended up with something that we can look at and analyze pretty simply from a quick glance. Okay, so we'll leave it there for today, and then we'll pick up with starting to think about forces and winds in the next screencast.